Now, I don't mean this in terms of the actual fundamental deep question that you guys talk about late at night in your dorm rooms or whatever, what's the meaning of life? But I mean it sort of literally, what is the meaning of the word life? And we'll get to that a little bit. But you know, if we think a little bit about what this course is, it's kind of a fun course because the title of this course, Life in the Universe, is supposed to evoke sort of a sense of wonderment, right? The kind of thing you might ask yourself when you look up at the stars on a dark, dark night. What is going on around those other stars? Okay, we know there's this sort of vast Earth that we live on with all the complexities, this great variety of life here we have on Earth. But as we'll learn about in a few minutes, the Earth is a teeny tiny place compared to the vastness of the universe. And the number of planets in the galaxy itself, and then by extension the universe beyond, is huge. We're talking hundreds of billions by hundreds of billions of opportunities. And so the question of life in the universe is to sort of start with what can we imagine might be out there? And in this course, we will then bring all we have scientifically to bear on that question to try to answer it in the best way we can. So starting off, of course, we don't know the answer right now. We don't have a scientific answer for is there life beyond the Earth. But this course is about what we know and how we're beginning to build a picture of trying to determine what the answer is. I wanted to open this up a little bit by sort of asking you, why did you take this course? So, does anyone want to volunteer why they're taking this? I mean, for those of you who are not taking this course just because you get some credit for it and it worked out your schedule, which is okay, are there people that are taking this course for a particular reason because they're interested in the question and what's the question you're trying to answer? Does anyone want to volunteer or something? So by the way, let me just start right now. I'm going to make a fool of myself every day up here, so you should not be shy about just talking. I really want this course to be something where people are comfortable just kind of asking questions because I got no real agenda in here other than to get you talking and we can have a fun conversation. Does anyone have burning, are you taking this course because you wonder if there's life out there? Yeah.
Yeah, I took the course because I find the title of the course itself interesting.
Yeah.
I want to see what information is there.
Cool. So it was the title that kind of sucked you in, and you want to know. You just kind of want to know, what do we know about life beyond here? Okay. Are most people in that boat? Okay. So I can tell you that why I created this course was, I think there's actually been a bit of a phase change over the last literally couple of years in our ability to address this question scientifically. 30 years ago, 100 years ago, 1,000 years ago, even more than 2,000 years ago, people were asking themselves the question, is there life elsewhere? Is there life on other worlds? And what would that life be like? So philosophically, this question has been with us for a very, very long time. But only within the last couple years have we learned something that's truly amazing. And what we've learned is that a large fraction of stars in our galaxy that we look up and we can see with some of them, we can see with our naked eye, have planets orbiting them. And not only do they have planets orbiting them, but those planets are a lot like the Earth in that they're the right distance from the planet star to have liquid water, so they could have oceans, they could have lakes, it could rain. This is a huge deal. Nobody knew this for sure 5 years ago. Only within the last 2 years could I stand up here and tell you this confidently. And so in that sense, it becomes sort of a phase change. Like suddenly there are all these endless opportunities now for life to exist elsewhere in the universe. And so it sort of motivates a deeper look at the question and then what we might do to actually, study these planets and see whether or not there might be life on them. Okay. So, I wasn't specific about this, but about 20% of stars in our galaxy, so we look up in the sky at night, every star you see by eye is in our galaxy. 20% of those stars, roughly, has a planet that's like the Earth, meaning that it's rocky, and that's important. So there's solid stuff to stand on. It's at the right distance from the star to have liquid water. As far as we know, water is probably the key ingredient for life on Earth. If life is actually common on these planets, and again, we don't know that for sure, but if life is common on these planets, there's a real chance that in your lifetime, we will detect that life. And part of this course is to talk about how would we do that? What would we be detecting and what would that look like? Another question that motivates this course is sort of this kind of maybe spooky question. Are we alone? Right? And what's meant by that, I think, what people think about, they're not talking about, am I alone or are there other bacteria floating around the universe? They're not talking about bacteria. What we're talking about here is intelligent life. Okay, we're talking about some kind of life that has evolved or emerged in the universe beyond the Earth that we can talk to. That's intelligent based on some definition of intelligence, but basically something that we can communicate with and have information exchange with. Okay. If we were to find this to be true, what would be the implications of this? Okay? What are the implications if not? So is it scarier to think that we're the only intelligent life in our galaxy / in the universe? Or is it scarier to think that there's lots of intelligent life elsewhere in the galaxy and the universe? If I could tell you for sure, yeah, we've just done this experiment, and based on this experiment, we're perfectly alone in the galaxy, what does that mean? Or if there's 5 other civilizations that are sort of like ours except more advanced, how would that change the way you think about yourself, we think about our planet, we think about the goals and what we're trying to do here? It's interesting to think about these things because it might change the way we think about goals for what it is we want to accomplish with our lives, for what are the purposes of countries on the planet. And so thinking about these things I think is valuable for many different reasons. What are the implications? How would this change philosophies, this world philosophies, this ideas of identities and tribal allegiances and things like that? How would it change things? I don't know. But it's hard to imagine that if we were to find evidence for life like this elsewhere, that it wouldn't affect people in a pretty fundamental way, at least people who are paying attention. Are there any questions or comments about this? So, if we back up and we look at the written record, and of course, this is a very specific kind of record because we don't really know what people were thinking when they were writing their thoughts down. Right? So for most of the history of our species, which is something like 100,000 years old, people weren't really recording their thoughts in ways that we can now look and read. So it's hard to imagine that people weren't thinking sort of very, bold thoughts 50,000 years ago. But the first recorded ideas we have about thoughts of other worlds come to us from the ancient Greeks. So these ancient Greek philosophers who more or less invented or were the pioneers of what you could sort of call science. This guy Thales is a really instrumental figure. He was living around the time 600 BC, so a long time ago, 2,600 years ago. And his student who was named Anaximander, who was his greatest student. They lived in a little place called Miletus here. It was an Ionian port city. And people living, so Miletus was this interesting city. It was sort of like a group of people who were kind of independent merchants, and they were sort of self-starters. You might think of it sort of like the caricature of sort of the self-starting person living in the Old West in the United States, or that kind of flavor. Thales had a truly radical idea. And as far as we know, the first recorded person who had this crazy idea, his crazy idea was that humans could understand the workings of the world in material terms. Using nothing but logic and observations of the world, human beings could figure out how the world works and why it works the way it does without appealing to spirits from beyond the physical world. This is a crazy radical notion, right? But within it becomes a lot of power. So let me just give you an example, right? So one of Thales' ideas was that the reason why we have earthquakes is that water is crashing into the earth and that shakes the earth. That was one of his ideas. This was my theory for what causes earthquakes. So is that right? Who thinks that's right? Okay, who thinks that's wrong? Good. Okay. We know that today is wrong. But herein lies the power of this idea, because we can prove it wrong. We can observe waves crashing into the ocean, watch that all the time, and if we ever have earthquakes when waves aren't crashing into the land, then we know that's not what causes earthquake. So you can rule out that hypothesis and move on to a different hypothesis. If your hypothesis was, however, that Zeus is mad and shakes the ground, it'd be very difficult to rule out that hypothesis. So the power of science is not necessarily in having the best questions to ask. It's being able to rule out whether or not they're acceptable. So having a hypothesis and ruling it out, that's what science is about. And it's amazing how simple that idea is, but if you have something that's testable and refutable, you can baby step that and learn a lot along the way. Importantly, Thales and Anaximander taught that the heavens, the stuff up there, the stars in the sky, the moon, and all that stuff, were composed of physical objects that were basically made of the same physical stuff that the earth is made of and that we're made of. Again, this was a radical notion. Democritus, who was sort of a follower, sort of a intellectual descendant of Thales, was living around the year 400 BC, so a couple hundred years later. He's a really amazing thinker. He proposed in 400 BC that there are many worlds that exist throughout the cosmos. And that on some of those worlds are life. He believed that everything, you and me, the rocks, the trees, the sky, all that stuff is composed of these little things that he called atoms. This is amazing, right? It's amazing that this person living 2,400 years ago came up with the idea of atoms. Came up with the idea that there's other worlds out there. Now, by the way, this was not accepted by everybody. And fundamentally, it wasn't accepted because basically you couldn't prove it right or wrong because there weren't great ways of testing it technologically. But the point is that the idea, this creative idea, was there. People who followed Democritus, by the way, were called atomists. And these atomists generally believed that there were many other worlds. They were all different, and the universe was filled with these other worlds. This idea of there being other worlds is in stark contrast to the ideas of a couple other fellows you may have heard of, Plato and Aristotle. Plato and Aristotle taught that other worlds are flatly impossible, that there's only one world and that world is unique, and that's the Earth. And that in fact the heavens, the stars in the sky, and the planets, they were composed of stuff that was very different than the stuff that the Earth is made of. They were made of heavenly perfect stuff that would last forever, that was unchanging and uncorruptible. Whereas the stuff here down on Earth was constantly changing, subject to decay. The Earth was the land of rot and death and war, and the heavens were this arena of perfection. Every object up in the night sky was perfect. But if you look around us here on Earth, there's just gross stuff everywhere. And the only place that there was death and life was the Earth. And they basically ridiculed the atomists for having this idea that these things up in the sky were somehow different. These ideas would hold sway for a long, long time and influence thought in the Western world and in much of the Muslim world for a very, very long time. By the way, this is flatly wrong, and this is a fundamental point of this course. The same laws, the same physical laws that govern stuff on Earth, remarkably, govern stuff up there in the sky. Right, so I can make the calculation for what it ought to be like opening a balloon as I drop my robot down to the surface of Mars. I can make those calculations based on experiments that I've done on the Earth, and I can shoot my rocket ship to Mars, I can launch a spaceship, I can land my robot and drive it around the surface of Mars. Okay? Well, what Aristotle had thought of that. Right? Around the year 1000 BC, people in other parts of the world were having similar conversations. Okay? There's a famous intellectual named Al-Biruni who was living in Central Asia, so modern-day Afghanistan, basically, is where he was living. He's widely considered one of the greatest scholars of all time, probably the greatest thinker since Aristotle at this time. He had some kind of amazing notions. So, for example, he was asking the theoretical question, are there other solar systems among the stars? Okay, this was like 500 years before Copernicus. He looked up at the stars and he said, those could be other suns, are there other solar systems up there? And if so, could there be life around those stars? He also also anticipated key points of geological evolution in the year 1000. And even Darwinism, to some extent, though actually not fully, this idea of even some sort of evolution or changing in life on Earth over time. He even suggested that the Earth could be spinning on its axis. Right? So even though it looks like the sun rises and sets every day, that's an illusion, it's not going around us. The Earth could be spinning on its axis, and that could be causing the sun to appear to rise and set every day. And his point was, he was very scientific about it. He basically said, look, this could be going on. We need to come up with ways of testing this idea. Experimental. Of course, the big revolution in Western thought happened around the year 1540 with Copernicus. Copernicus had this, in many ways, a radical notion that was not that much different than what people like Biruni were thinking about. But the sun is actually the thing that's at the center of the solar system, and everything is going around the sun. Now, eventually, the reason why this was so important, and the Copernican revolution actually happened, was a convolution of things, right? Roughly at the same time Copernicus was doing this, there were advances in technology that would allow us to actually discriminate between the idea that the Earth is sitting still, or the sun is sitting still. Turns out those are really hard things to tell apart. You need really precise observations to do it. And not too much later, Galileo Galilei built himself a telescope, and with this telescope he saw things that no one had ever seen before. And fundamentally it was with those observations, with a piece of technology that did not exist anywhere in the history of the world before this time, that he was basically able to say, yeah, it looks more like this picture than the idea that the Earth is fixed. Pretty soon after that, the idea of other worlds began to explode in Western thought. Giordano Bruno, for example, was a very famous early proponent of other worlds. Right? So here's a quote from one of his treatises on this. Space we declare to be infinite. So he says, look, the universe is infinite. And if the universe is infinite, right, in it are an infinity of worlds of the same kind as our own. So he was a big proponent of the idea that, look, the universe is filled with these other worlds. Because it's filled with these other worlds, there's probably life elsewhere in the universe. By the way, this is pretty bold, right? Because all they knew is that there were other suns. They had no detections of any other planet, but they just sort of took it for granted that there should be other planets out there. By the way, this guy was not an easy fellow. He was very bombastic. He wasn't really so much a scientist as a philosopher. And he really rubbed it in everybody's face that life had to exist elsewhere. The Catholic Church did not like this. And they eventually burned him at the stake around the year 1600 for these views. The point is, it was a view. Okay, he had no proof. He had no absolute scientific proof that there was life beyond the sun. And we don't today either. Right? And so this becomes an area of conjecture. So we even played this game a little bit with the rocket mix module. This is a question that we asked here. So it's kind of fuzzy, so let me just remind you what it is. Which of the following describes your current belief about life of any kind in the universe? So this includes life of any kind, very primitive life or advanced life, whatever. It can be any kind of life in the universe. And these were the percentages of what people answered. About 93% of you believe that life of some kind exists elsewhere other than the Earth. Maybe about 7% of you say, no, Earth, only place in the universe that there's life. About 75% say it's somewhere else within our galaxy. And about 20% say it's not within our galaxy, only in other galaxies. About 17-18% of you think that it's elsewhere in the solar system itself, which if so, that would be very exciting. So I don't know which of these is correct, but we don't know. Intelligent life, what about intelligent life? So about 78% of you believe that intelligent life exists somewhere other than the Earth. There's some other ETs, there's some ET out there. Most of you think that it's not within our galaxy, though. You think it's other galaxies. But about 35% say it's somewhere else in our galaxy. And a minority, but not such a teeny tiny minority, say that Earth is the only place in the universe with intelligent life. By the way, who is in here to subscribe to this opinion? I think this is totally valid. It's probably closer to what I think, actually. Only 1%? So the 22% is totally off. Really? Only 1%. Okay, so the question is there intelligent life elsewhere in the universe? Okay, and the question is, the answer is, how many of you believe that the answer is no? The only place that there's intelligent life is Earth. Raise them high, I can't see. Okay, that's about 20%. Good, okay. And how many are the other way? They think it's all around us. Does anyone think there's anything on Mars that's intelligent? Good. That would be crazy. So for the 20% who raised your hand about the Earth being the only place that there's intelligent life, which is a totally valid opinion. That's good. That's legitimate, right? And we'll talk more about that later. Imagine the responsibility you have, that we have. There are 100 billion stars in our galaxy. There are 100 billion galaxies in the observable universe. So 100 billion times 100 billion stars. And there's one planet in the universe where there are people who are capable of looking up at the sky and figuring it out. Trying to attach real meaning to what we have, right? We, in some sense, are the universe looking back at itself, right? So we are the single, only intelligent species in the entire universe. We better get it right. So what are we doing with our time? And if we're not, what do those other intelligent people think of us? Because they can see what we're watching on TV. Those signals go out. So here are our results, okay? But let's remind ourselves of something. This is our democratic poll of this course. We might as well just lead, right? This is the answer. This is not science. So now what we're going to do is are fun questions. We've all tried to answer them in a subjective way. What if we wanted to get an actual concrete scientific answer? We wanted to frame some of these parameters in these questions and try to come down, try to actually get an answer. How do we go about approaching this, right? So that's what this course is about. Okay. So for example, you can have, science is about ruling out hypotheses. I talked about this before, right? Science is not about telling you what the right answer is. Science is about telling you what the wrong answer is. Science is very good at telling you what the wrong answer is. Nope, that doesn't work. Nope. So for example, you have a hypothesis, life exists on Mars. Or you can have another hypothesis, intelligent life exists on Mars. How would we go about ruling out those hypotheses? How do we test them? What kind of life? Are there fish on Mars? How do we test that? Well, fish require water. Is there any liquid water on Mars? Nope. Okay, that kind of thing. The subject is hard. So this general subject is called astrobiology. And it's a hard subject because it combines lots of different kinds of science. But in that way, it's very fun because it allows you to kind of dabble in all of these different kinds of sciences, which all in themselves are all really interesting. And apply it to a question that's super awesome, which is, like, is there life outside the universe? Which is a cool question. So it combines, we have to know something about biology, like we talk about life, but we have to know something about astronomy, like learning about life from things that are far away in the heavens. Planetary science, so we have to understand how planets form, the diversity of planets. Earth science, right? How did the climate on the Earth develop? How long did it take for life on Earth to develop, that kind of thing. Chemistry, right? Because chemistry fundamentally is the backbone of biology. So if biology was to emerge on the early Earth, it's really complex chemistry that allows that biology to happen. And then finally, the thing that brings all this stuff together is in fact called astrobiology. So we're going to be doing that in this course. And all of these subjects obviously are sort of like majors in and of themselves. But what we're going to do in this course is just kind of dabble along. We're going to sort of touch each one with a fast overview in the way that we need to in order to approach this question, right? And I've tried to set it up in a way that's fun. I'm going to try to take sort of the best of each, the fun parts of each of these fields, kind of bring them together to answer these questions. This is the big picture. And let me do this. I'm always worried people are going to go to sleep when I do this. Let me just do this. I'm going to turn back on too. So I'll go to sleep. I'm going to turn back on. Then it looks cooler like this, right? So look, when you look up in the sky at night, on a really, really dark night, if you go out someplace really, really dark, like say Easter Island, okay, and you look up at the night sky, it is breathtaking. Stars fill the heavens. And you see something else too. You can see that there's sort of this concentration of stuff in a band, and that band kind of runs in an arc overhead like this. That's called the Milky Way. How many of you have seen the Milky Way with your eyes? Take your eyes. Wow, maybe 5-10% of you. That's not very many. Great. If you haven't seen it, you should go camping. Go out someplace far away and look at it. It's really cool. 100 years ago, everybody saw the Milky Way. It was this dominant band of stuff overheads, right? And when you see it from Earth, it sort of looks like this, right? And people have been seeing it for thousands and thousands of years. Right? I mean, I love this picture from Easter Island. You can imagine this ancient Polynesian culture living on this island, building these amazing statues, and overhead they see these stars in this great band of light. This is what we see. The reason why we see this is that we're actually embedded in a vast, vast disk of stars that we call the Milky Way. We are about halfway out. We live here in this outer spiral arm here. And the reason why we see it as a band is because we are living in this disk, okay? If we look up out of the disk, there aren't as many stars. But if you look in the plane of the disk, all that light piles up, and they all kind of stack on top of each other. It's like in the same way, if I look this way, I see lots of people, and if I look this way, I don't see as many people. Right? Because there's just more people in this direction than that direction. It's the same way. So here you're looking through the disk, into the plane of the disk. Up here, every single star you see by eye at night is in our galaxy. It's just that these stars are up or down from our location in the disk. Does that make sense? Does anybody know how many stars you can see by eye? Yes? You ever counted them? What?
Around 4,000.
Around 4,000. Very good. Yeah, that's right. A few thousand. In fact, over the whole sky, over the whole Earth, on really dark nights, you can see about 6,000 stars. That's a lot. Now, let's go back to the Milky Way for a second. The Milky Way has 100 billion stars or more. In fact, about 200 billion stars. In fact, every star you can see by eye at night is within this little bubble right here. So even though it seems like there's a countless number of stars in the sky, you're just at the tip of the iceberg. You're talking about the number of stars in our galaxy. Okay. Right. So there's lots of them. Lots of stars out there. And by the way, these stars are old. A lot of them are very old. Our sun is about 4.5 billion, 5 billion years old. That seems very old. But there are stars in our galaxy that are 10 billion years old. Twice as old as our sun. Now what do we take from this? It took about 4.5 billion years for us to happen on Earth. There are stars out there that have a 5 billion year head start on us. So if you think that life is common, that means there are, in principle, places out there that have had a 5 billion head start to start making life. 5 billion years is a long time. Again, our species is only 100,000 years old. Oh, and there's 100 billion more galaxies in the universe than this. So there's lots and lots of options. However, this is the only known site of biology in all the universe. Another thing we know about the Earth is that life seemed to emerge on Earth about 3.8 billion years ago. This is about as fast as it could have possibly gotten going. Before this time, the Earth was hot, really hot. It was being bombarded by all kinds of heavy, big things. It was basically a molten ball of lava. And during that time, there could be no liquid water. But as soon as the Earth cooled down enough that it could have liquid water, we see evidence for life, like right away, like that. Now, what we don't know is if biology normally starts this quickly on a planet. All right? Rerun the movie again. Make the Earth happen again. Change a few random seeds in your simulation. Change a little this up, a little that up. The life will emerge that quickly. don't know. But if we're typical, then you might imagine that every time you get something that's kind of like the Earth, very soon after the thing forms and gets some liquid water, life starts happening. If the Earth's typical. Another thing we don't know is whether or not there are universal laws of biology. Okay, we know that there's biology on Earth, and we have, the field of biology is awesome. It's so complex. There's so much going on in the field of biology. But biology is all about biology on Earth by definition. And we don't know if the general laws that have been derived based on understanding biology on Earth are applicable throughout the universe or not. What are the things about biology on Earth that we think might be similar to biology elsewhere? I mean, for example, the molecular instructions of life are encoded into the DNA molecule, right? We've heard of this. Does it have to be DNA? As we'll learn later, there's 4 base pairs in DNA. Does it have to be 4? Could be 2. Could you have life that way? If so, what would that look like? Another question that we'll talk about is intelligence, right? Is intelligence like ours inevitable in some kind of evolutionary process or not? There's arguments on both sides, and we'll get to that. We don't know for sure. There's certainly strong advantages to being smart. But there's also huge disadvantages for having such big brains that we have to feed all the time, right? I mean, it's like so much of our calories are wasted on our brains. Right? If all you want to do is have life, like why do you have this big brain? So our big brains can be like peacock tails, like not inevitable at all. Just some weird evolutionary freak thing that happened, and we just evolved in a way that we like other people with big brains. Okay, and our babies have big brains, and it just happens that way, somehow, right? Another thing we don't know is liquid water necessary? And I'll bring this back in a second. We think probably so, just based on Earth. One of the ways we start looking at these kind of questions on Earth is looking at populations of creatures that survive in really, really extreme environments, right? So we know that there's life everywhere. You walk out into a place where the temperature's pretty mild and there's lots of water and whatever, and you've got like forests and rainforests just filled with life. But there are creatures on Earth that live in really, really extreme environments. I mean, one of the coolest ones is this thing called the tardigrade, which is called a water bear. This is a blow-up of what it looks like. It's this microscopic thing. They're smaller than a millimeter in size. Okay? They can survive crazy, extreme harsh environments. They can live in little droplets of water, but if you take them out of water, they can kind of hibernate effectively and live for a long time without that water. They've survived 5 mass extinctions on Earth in the harsh conditions of space. We've done experiments. We've watched these things up into space, and they just survive for months in the vacuum of space. They come back down and drop some water on them, and they're like back. Right? So there's stuff like this on Earth. You're like, wow. Okay, these things are pretty robust. So life is pretty amazing, if you give it this variety. We know that there's different kinds of life that thrive on Earth at a huge range of temperatures, from basically freezing water, the point you have any liquid at all, up to boiling water at 170 degrees Fahrenheit. There's life that lives in water that's that hot. Huge radiation levels. They can survive strong radiation. They can survive high levels of acidity in water, right? And fundamentally, as far as we can tell, that all you need for life on Earth is water. If you have liquid water, you find something living in it. And so in astrobiology, sort of a simple rule of thumb that people go by is if you have water, it's a good place to look for life. And in fact, when I talk about habitable planets, I'll talk about the presence of habitable planets around other stars. These planets live at a right distance from their stars to have liquid water. That's why we call them habitable, because we think water is that important. Now again, it may not be. You may be able to do it with some other liquid or something else, but that's sort of a starting point from where we are. What about our solar system? We play with this idea, like maybe there's life elsewhere in the solar system, wherever we want to look. Now, a really interesting place, by the way, is Mars. We actually have a lot of evidence that Mars in the past had flowing liquid water. We now think that Mars may have had vast oceans billions of years ago. Today, it's extremely dry. Mars is a very, very dry and cold place. It's basically like a cold desert with a very thin atmosphere. But it has frozen water underground. And so a lot of people think of Mars as like this place we can go and study geologically, because it had liquid water in the past, and you could find evidence that life was thriving there 3 billion years ago. That would be a profound thing, right? Because then you would know, hey, it happened twice. If it happened twice, then what are the odds that that's rare? So then you start thinking, boy, that is pretty common. And then something drastic happened on Mars that we'll talk about in this course that basically allowed it to lose its atmosphere. It now cannot sustain liquid water, and it basically died. Another place that's very exciting, actually, you might not first think about it, are moons. So I'm not talking about the Forest Moon of Endor, the Star Trek thing, or Star Wars fans. This is a real moon. So this, for example, I'll talk about this one. It's called Enceladus. It's a moon of Saturn. Enceladus is this crazy cool moon, right? Because it's got liquid water. It's this frozen ice ball. The outside of it is frozen solid. And it's going around Saturn. But it's going around Saturn in such a way that the tidal field of Saturn is kind of squeezing it. And by squeezing this ice ball, it's creating liquid water underneath, providing energy to it and heating that water up. This is a picture of basically water geysers shooting off the surface of this moon. That was taken by the NASA Cassini spacecraft. And so we know that there's got water geysers pouring stuff out of here. It has a vast liquid ocean. In fact, it's probably got more water underneath its ice caps, underneath its ice, than all the water on Earth. There's probably more water in this moon than there is on the Earth. It's just under the surface. So you can think of it as sort of a deep Arctic ocean beneath layers and layers of ice. But on Earth, we think there may be life in such oceans. So there's an idea that there could be life swimming around, maybe even, underneath the surface here. We know there's organic material. There's a source of heat from these tidal forces. So this is a really interesting place where scientists want to send missions to try to get in there and see what's going on. And I'll talk more about that in this course too. Are there questions about this? Yeah. There's another moon that's called Europa that's also very interesting. There's a lot. It turns out that there's lots of big moons in the solar system that are like this. So if you've read about Europa recently in the news, it's another one of these things that we think has a potentially life. And I'll go through the moons of the solar system later, but it's just one sort of one-off idea. And of course, I talked about this before, the Milky Way has lots of options beyond the solar system. Okay, 200 billion stars, roughly 40 billion habitable planets, meaning that they're the right distance from their star to have liquid water. Okay, so the idea is that there's this thing that we call the habitable zone. If you're too close, you're too hot. If you're too far away, you're too cold. If you're in the middle, you're habitable. this is very tough business because it turns out the temperature of a planet depends crucially on what the atmosphere of that planet is. Right? If you took away the Earth's atmosphere of warming, okay, the greenhouse effect on Earth, all the water on Earth would be frozen. So you need to know something about the planet's atmosphere if you want to really have a very good understanding of what its temperature is. So all of this has to be factored in when we think about that. The point is, it's possible that there are about 40 billion planets in the galaxy that can host liquid water. Now, we talked a bit about this before, but people have for a very long time charted the sky and thought hard about what's going on up in the sky. This is a cool picture. So this is a picture of, I'll turn it down again. Speakers will see. This is a really cool picture. This is one of the most ancient temples in Delhi in India. It's an ancient tomb in Delhi in India. So we're seeing the night sky up here. This thing was built circa 1230 AD. So a long time ago, but we would think it was ancient. And I love it because you can see a very familiar constellation up here. Does anybody know, I'm circling it here, does anyone know the name of this constellation? Yell it out. Orion. Does anyone else see Orion there? I'll show it to you in a second. This is Orion's belt. This is like Orion's sword or whatever, and this is his armpit there. There's other stuff going on. This stuff is kind of harder to see. Does anyone know what Orion's facing? This constellation here, does anyone remember? There's something called Taurus the Bull, and Orion and the Bull are fighting. And over here, there's a little star cluster called the Pleiades. Okay. So here's Orion. You can't really see it. Here's Taurus. I mean, you got to be creative. Like, okay. Understand these people had no TV. They didn't have anything to do. They were just looking at the sky. But whatever. But people living a long time ago who looked up in the sky, they saw these patterns and they studied them, and people have been doing it a very, very long time. This image was taken over a temple that was built in the year 1200. We think of that as old. But in fact, the earliest known depiction of a big chunk of the night sky actually comes to us from 1500 BCE in this tomb here, which is basically in Thebes. It's the tomb of Seneca. And it's a depiction of the stars in the night sky. And right here, taken from the wall, or I think it's the ceiling of this temple, of this tomb, is Orion fighting a bull. Okay? The thing that's mesmerizing about this is, the dates kind of run together, okay? But imagine the Roman Empire, right? You think of the Roman Empire as like, wow, that was a long time ago. The Roman Empire at its zenith, that was happening in the year about 250 AD. That's halfway back to this. Okay? So the ancient Romans, when they thought of these people, they thought of them in the way that we think of the ancient Romans. That's how far back it is. And yet they have these precise maps of the sky. They have constellations that are, sort of in a similar lineage to those that we have today. So people a long time have been looking at the sky and thinking about the stars. Here's another example from central Mexico, from AD about 1300. Right? This is an Aztec image from a star cluster. It's in fact that same Pleiades that I showed you before. You wondered why I showed you that. There was that little Pleiades, this thing here. You can see this with a nice bit of binoculars. You can see this. Oops, that was a giveaway. They saw it too, right? They called it the gathering place. It was a group of about 7 stars, and they called it the gathering place. For us, the Pleiades are called the 7 sisters. Okay, so it's a gathering place, and so the Western tradition of mythology, it was, a group of people, a group of things in the Western tradition of astrology. It was also a sort of tradition of gathering place in the Aztec cosmology. Right? And this star cluster is seen all over the world. I mean, so one of the amazing things about these things in the night sky, right, is they unite us culturally and in time too. These are different epochs, right? These are different time periods in different parts of the world, but they're studying the same things in the sky, and those things are important to these people. Right? You're probably familiar with this. I flashed it before. But Subaru means unite, right? And the Subaru label is the Pleiades. Right? In ancient Japanese culture, they also recognize the star cluster as interesting. And the Subaru car company has adopted it today, and there's a constellation on the back of those cars we've seen driving around. So the point is that these things in the night sky kind of are sort of uniting to us as, across cultures, across times. And I think that's a very important thing. I think that's one sort of theme of this course. Right? We are on the Earth. All of us are on the Earth. We all live on the same planet. We came about on the same planet. And we're trying to make sense of things that are far away. And thinking about what a potential alien culture would look back on us and think about is an interesting thing. It's an interesting exercise. Now, the other thing that kind of pervades our culture is science fiction, right? The idea that there might be sort of aliens out there and what they would think of us, right? This is something that's non-trivial. And I don't want to talk about it too much, but it's interesting to sort of put it in perspective, right? So in fact, this is the first depiction we have, sort of a lot of people think the first example of sort of science fiction comes to us from Lucian from the world from the year 160 AD. So again, very, very ancient. And in this story, there's this idea that there were intelligent life on the moon and the sun, and these people came to Earth. Right? Now, the purpose of this was actually a commentary, right? So the purpose of this was basically to make fun of the Greek tradition of writing histories as being, like basically treating mythology as truth. And so this was actually supposed to be kind of a satire against those mythologies. Here's another example from the 10th century Japan called The Tale of the Bamboo Cutter. This is a really neat idea. Again, a long time ago, but the idea is this bamboo cutter sees a glowing piece of bamboo, slices it open, and inside he finds this tiny little girl. And she's beautiful, otherworldly beautiful. And she grows up with, and it turns out you find out later she's from the moon. So she's sort of this moon goddess princess that came down for whatever reason. And she grows up with this otherworldly beauty. She's courted by all the men in Japan, and the emperor eventually, wants her to marry him, etc. But she doesn't. She says, no, she sort of understands she's from another world, so she doesn't do this. And one day her real family comes back and carries her back home in a celestial carriage. But again, this speaks very much like a modern day sort of science fiction story. And in fact, it's interesting to read up on this. I don't have time to go into it, but the word Fuji, Mount Fuji, is fundamentally named after at least a myth that's incorporated into this story associated with immortality. So it's worth your interest in it. You should read up on it. It's an interesting idea. Another thing that you probably are familiar with is the 1001 Nights, or what's often called the Arabian Nights, this collection of stories from sort of Central Asia that were grouped together in the 14th century. One of the stories that maybe you might not be familiar with is this one, The Adventures of Bulukiya. This is interesting because this protagonist is looking for immortality and searching for basically the herb of immortality. This person is traveling all over the world and eventually travels all over the universe and encounters all kinds of alien beings and mermaids and stuff like that. Right? So the point is that there's ideas about life beyond that pervade literature in lots of different cultures. Right? This idea has been with us for a long time. Cyrano de Bergerac is another one that has this kind of interesting story, States and Empires of the Moon, where he talks about four-legged creatures from the moon. And this, again, is sort of a satire type of story. A very famous one is H.G. Wells with The War of the Worlds. This is sort of the archetype of aliens as invaders of Earth. Right? So you've probably heard of The War of the Worlds. There have been lots of movies about it. This was a book in 1898. Martians are invading the Earth to escape their dying planet. Right? And eventually they die off because they get some kind of disease that they don't have immunity to, and they die away. Right? Now, this was interesting because it really resonated with the British anxieties at the time because they were an empire in decline. And this was speaking of their own fears about being an empire that was now sort of waning in the face of this thing going on across the Atlantic. Later on, Orson Welles did a radio broadcast of War of the Worlds in 1938. You may have heard that this created this crazy uproar. How many people have heard of this? Yeah, if you haven't heard of it, it's a very interesting. So he does this radio broadcast, right? But it's done sort of straight. So at the very beginning, he's like, they're like, okay, this is a story, this is a fictional account. But the thing starts off like a radio broadcast. Martians are invading New Jersey, everyone run, or whatever. And people freak out. There's like mass hysteria because people are hearing this and they think it's real. This was sort of resonating with anxieties that the U.S. was already having because it was pre-World War II Europe, and they were worried about invasions anyway. And so there was sort of anxiety within the culture in the United States that some kind of invasion was imminent. And so this sort of resonated with that. In 1953, the first film of War of the Worlds was made. It's got an Oscar for special effects. I mean, if you look at it now, it's not that impressive special effects, but at the time it was a big deal. This time the Martians were invading Los Angeles. Okay, and they used stock footage from World War II destruction and warfare, and this was resonating with anxieties about atomic war. So you see these stories reinvented but then brought back into the cultures that sort of are associated with what we're worried about now. The most recent one, I think this was the one with Tom Cruise, the Steven Spielberg 2005 movie. They're back to New Jersey again. Again, this thing is like so 9/11. It's just very much built around. It's sort of small picture, and there's just so many things that sort of resonate with the existential fear of terrorism post 9/11. So you see this kind of again and again that people take these stories of aliens but then incorporate them into what people are thinking about themselves. So while I don't want to deny the existence of aliens in film, aliens in art are probably teaching us a lot more about ourselves than they're teaching us about any realism about what aliens might be like. And so that's what I want to touch on sort of here. But what might we actually expect of aliens? And by the way, this is not necessarily a bad thing, right? Because here's a quote from Alexander the Great, okay? This great conqueror, Alexander the Great, who took over this huge landmass and was sort of this valiant, amazing leader, right? Sorry. His quote is it not? Oh, so he started to cry. When Alexander heard of the infinite number of worlds, he was talking to these philosophers who were convinced that there were infinite number of worlds. When Alexander heard of the infinite number of worlds, he wept. When asked why he was crying, he said, is it not a matter for tears that, when the number of worlds is infinite, I have not conquered one? So you get this interesting perspective, right, where you have supreme conquerors, supreme leaders, right, who have their entire identity is based upon them controlling some section of land on the earth. You then take a step back and realize that all of what you're doing is on this little dot within this vast, this vast universe. But what might we reasonably expect from these aliens? Well, let me flash just another example of what people are thinking aliens might be like. This is Voltaire's Micromegas. This is from 1752. So again, I'm just reminding you that these ideas have been around for a long time, and the great Voltaire wrote about it. And his depiction, Micromegas, is a 20-mile tall visitor from a planet that lived around the star Sirius. Okay? And he's got a companion from Saturn who's only like 1,000 feet tall or something like that. I can't remember, but his companion is not 20 miles tall, but like a mile tall or something. And the whole point is that they come to the Earth and they first realize, they first think there can't possibly be life here on Earth because it's just so tiny. And they finally realize that these little microscopic things that are yelping at them are actually people, and they have intelligence. And a lot of it is a satire about sort of self-importance of people. But I want to talk a bit about this idea that you have 20-mile tall visitors and whether that makes any sense. Okay? Something that you might be a little bit more familiar with is this one. Okay? So I'll call this alien too, right? We got these giant gorillas, we got giant people, we've got our King Kongs. And you take a look at what King Kong looks like. He's taller than the Empire State Building. This is a weird perspective, but she's also taller than the Empire State Building. But yeah, we have this giant gorilla thing. And the question is this reasonable, right? Would a giant gorilla really look basically like a gorilla? Okay? And we can use physics to answer this question. So one thing, this was an idea that actually first came to us from Galileo Galilei. He said, have you ever noticed when you look at the skeleton of a mouse and the skeleton of an elephant, they don't look the same? Does anyone notice what's different here? What's different? What's different about, say, the front leg bones of this elephant and this mouse? Yeah?
Legs are bigger.
Good. The legs are bigger. The legs are thicker. See how thick that is? So an elephant is actually not just a mouse blown up, but the legs are thicker. The elephant is a much stockier thing than a mouse. You see that? Galileo made this point in 1638 when he said, look, if you ever look at the bones of big creatures versus small creatures, you'll find that they're not just blown up versions. You can't just take a bone of a mouse and blow them up to the size of an elephant because they also get thicker. Okay? So the structure of animals changes as you make them bigger. Why is this? Well, he said, well, the first thing I have to think about is the weight that a structure has to support, right? The mass that something has to support is some density times its volume. Now, the mass of tissue is all the same, basically. All animals have a density that's basically that of water, more or less. So let's not worry about that. So basically, the mass of an animal just goes like its volume. Okay? And it's something times its volume. Now, another way to say it is that the mass is proportional to its volume. So as the volume doubles, its mass doubles. As the volume goes up by a factor of 10, its mass will go up by a factor of 10. All right? So, if you take something that's size L, now here's something interesting. The volume goes like the size of something cubed. Right? So if you have a cube of length 1, and you make it a cube of length 2, the volume of that thing goes up like L times L times L. Right? So think about it this way. The volume of a sphere is something like pi, it goes something like R cubed. It's some combination of pi and numbers that you can never remember, and then R cubed. Right? The surface of a sphere is some combination of pi and numbers times R squared. Right? You sell area, and you carpet your floor in square yards or square feet. Okay, that's square. Area is square, volume is cube. Okay? So when you measure something's volume, you have to take its rough length and cube it. Okay? So if L goes to 2, its volume goes to 2 cubed, or it's 8 times bigger. So compared to something that has a size 1, so you make it have size 2, its volume is now 8 times bigger than it was before. So you double its length, its volume gets 8 times bigger. So therefore its mass gets 8 times bigger. Right? So the mass, therefore, is proportional to the length cubed. This is important, right? Because if you take a gorilla and you make it 2 times its size, its mass goes up by a factor of 8. If you make it 3 times its size, its mass goes up by a factor of 27. If you make it 10 times its size, its mass goes up by a factor of 1,000. That's a lot of mass. Now, you might ask, what are you talking about here? You were talking about bones and now you're talking about cubes. Well, the strength of a bone goes like the cross-section of the bone. Right? So that's how much the bone can support. And the cross-section of the bone is just the area of it, and that goes like the size squared, not the size cubed. So weight goes like the volume, which goes like the size cubed, but strength goes like the area, which goes like the size squared. And so if you have a mouse bone and you make the mouse 10 times bigger, but you don't make its bone thicker, right? The mouse will weigh 1,000 times more, but the bone will only be 100 times stronger, and that bone will just break. So if you want to make a big elephant-sized mouse, you better make its bones get bigger too, in a different way than it's just slick. See what I mean? So bones have to get thicker as animals get larger. And so this thing right here would just be crushed under its own weight. This would not be a very scary animal, because it couldn't move. It would just like, it would just break, because it doesn't have thick bones, right? If you want to make a realistic-looking King Kong, it would be, something like this. Okay. So the point here is that as we imagine what aliens might be like, there are physical limitations to what they can be. Okay? And those physical limitations we can derive based on laws that we understand. Basic physical laws that can tell us that there is no 20-mile-tall creature from Sirius that's ever going to visit us. If it was 20 miles tall, it would be a very different kind of thing. So we are running out of time here, so what I'm going to do is I'm going to leave this question for next time. So the next thing we're going to do in this course is we're going to move on to talk about what is life, and we're going to define life, because then we're going to be moving on to talk about life in the universe. All right, thanks. So this is lecture 2, and this lecture is going to be about basically our discovery, a very, very quick introduction to our discovery of our place in the universe, so specifically the Copernican revolution and the process by which we basically figured out that the Earth orbits the Sun. And as soon as you have that, that really sort of blows the doors off our conceptions about where we sit in the universe. This movie that's playing in the background is something that was produced by the Museum of Natural History. You can find it, if you want me to show you where you can find a copy of this online, I can do that for you. But it's really an amazing thing because it puts together a lot of real data that we have about the Earth, the other planets orbiting the Sun, and it puts everything into scale. So what you're seeing now is a fly-through in this movie. It started off at the Himalayas and backed out, and it showed the planets orbiting the Sun, and now it's zooming out past our galaxy now. Every one of these little green dots is actually another galaxy and these galaxies fill the universe. So what this represents is one of the largest maps, real maps of the universe that we've ever made. So this is a real map of galaxies. The reason why it has this weird shape is it's a selection effect. It's just the part of the universe we've been able to survey. And then what's coming out now is this kind of green ball is basically the edge out to which we can see. It's not the edge of the universe, but it's basically the limit out to which we can see in the age of the universe. It's the distance light could have traveled in the age of the universe, more or less. And so we live in a vast, vast universe that's filled with billions of galaxies, and the start of this lecture will be sort of tippy-toeing into how we got this picture, so how we were able to develop this picture based on simple reasoning and then eventually technological innovation that allowed us to do this. And the other thing that I will talk about after that, something I didn't get to last time, is thinking about life and how we define life in this quest to sort of understand life throughout this whole giant universe of ours. Yeah?
So, in that connection, I see that we have more information regarding life in the two areas, and the other two are kind of more niche. Is that the reason why we have more?
Yeah, so I was trying to say this before, that basically there's just parts of the sky we haven't studied in great detail. So what you're seeing is, you see these sort of like bands that cut across the image. Think of a telescope, like literally what's going on is someone has a telescope, or a group of people have telescopes, and they're pointed at one spot in the sky, and effectively you drag it over and measure as much as you can along a very teeny tiny line. If you've ever looked through a pair of binoculars, you know how the field of view is small, and you got to kind of like find the thing you're looking for. It's like that with these big telescopes. They tend to have very, very small pieces of the sky that they can see very well. In order to map out big regions of the sky, you're basically going here, and then here, and then here, and then here. So basically we just haven't mapped out the whole universe to that depth yet, although there are plans right now to do that better. Another part of it that makes it difficult is we live in a disk of stars. We live in this Milky Way galaxy that's a disk, and it's easy to see stuff that's, if you're in a disk like this, it's easy to see stuff up here and down there, but stuff that's kind of in the same direction as the plane of the disk is hard to see. And so sort of our view of the universe is actually blocked along the directions of the galaxy that we're sitting in, but we can see out of it and into it. And so when you see maps like this, they're a little bit deceptive because they're trying to be realistic and show you real data. It looks like the universe has these big gaps in it, but we think that's the limitation of what we can see. Okay. That's a good question. We'll come back to this kind of stuff later in the course. So part one then is what we're going to call the Copernican revolution. And this was attributed to Copernicus, this idea that the sun is actually at the center of the solar system and the planets orbit around the sun. It's a pretty radical idea, actually, because, in fact, if you think about what the universe looks like, that is what the universe looks like to you, okay, if you go outside on a clear day and you look around, the world, okay, the universe that you see, that you're sort of out in, actually looks something like this, right? I mean, when I go outside and look around, it looks like the sky is a dome. I'm sitting on flat land, and it looks like there's basically an edge. So at some level, the universe, as we see it, right, from here on Earth, basically looks like we're in the middle of a giant snow globe. And in fact, this idea that the universe was basically flat ground, canopied by sort of an arching sky, is something that a lot of people sort of took for granted for thousands of years. As far as we can tell, many ancient cultures basically had this idea that this is pretty much what the universe was like. And in fact, if you think about it a little bit, and imagine that you've never seen pictures of the Earth from space, right? You don't have the ability to travel really long distances. This is not a bad starting point. In fact, this is kind of what it looks like. Okay. And it's interesting to ask yourself, let's say you were transported back in time, 4,000 years ago, and you could somehow talk to people, and they could speak English somehow. How would you convince them that this was wrong? Okay. Does anyone have any ideas? What would you say? You can be like, sorry? Okay. What does that mean? What do you mean by math?
I'm not a physics major.
You're not a physics major? Yeah. These people you're talking to aren't physics majors either. There's no physics 4,000 years ago. So do you believe that this is true? Okay, why not?
Because the sun differs. Right, like the moon?
The moon? Yeah. Okay. All right. So we got the moon. Who's doing this? They say, yeah, the moon. Yeah, we got the moon. We figured out the moon. The moon is a thing, and it goes around us like this. Sometimes we can see it in the day, sometimes we can see it at night, but you're not convincing me. First of all, you tell me from the future. I'm not buying that. And second of all, you tell me that what I see with my naked eye doesn't make sense, right? Any other ideas? Yeah.
Go on top of any building and look at the next capital over. You can't see it.
Go on top of any building and look out to the next...
To the next city. You can't see the next city over.
Okay, so first of all, it's 4,000 years ago. But we'll pretend there's some big city. There probably were some reasonable towns.
There's got to be some capital city. The next capital city over, you can't see it.
What's because it's far away?
Exactly. But it's because the world's round. If it's flat, you don't see it.
But if something's really far away, it's hard to see. I mean, I'm playing the role of someone 4,000 years ago, right? I mean, if something goes really far away, it's hard to see, whether it's flat or round, right?
It's hard to see. It's invisible. It's not there.
So now I'm going to start thinking you're crazy. You're telling me that things are invisible, but they're really far away. Right? I mean, I'm just playing with you, right? I'm not trying to be a jerk. I'm just trying to say, look, I'm someone living 4,000 years ago. You're telling me that I live on something that's round, which clearly doesn't look round. I see this, and you say, yeah, but the reason why you can't see stuff that's really far away is because the Earth is round. And my answer to that would be, well, when stuff is really far away, it's hard to see because it's dim. It's hard to see when stuff is far away. Any other ideas? Yeah?
Shift more over horizon, kind of thing down.
Okay, all right. I have a secret suspicion that you've heard this before, but this is what she said. She said, well, let's say you're standing somewhere, and you're near the water. And we've invented boats. Okay, let's say we're an advanced civilization 4,000 years ago that's invented seafaring boats. And they sail out into the horizon. As I watch them sail out on the horizon, the last thing I see of them is the tip of their sail. The first thing I can't see is their hull. Then I can't see the middle of their sail. And then finally, it's the very top tip of their sail that I can't see anymore. So if you look at that, it actually looks like they're curving off in the horizon. That's good. That's very good. I have a sneaking suspicion that you've heard that somewhere before. People get that? That's a pretty subtle argument, right? But, and it's kind of the same thing where it's like, imagine you're hiking with your friends and you're up on a mountain, and you got someone who's going fast, you're tired, you're like lagging behind, your friend is out in front of you, and if they go down a hill, the last thing you'll see is their head go down, right? The feet will disappear and their head will go down. That's sort of what distant ships look like when they sail off on the horizon. Okay? That's a pretty subtle argument. And again, then someone 4,000 years ago would say, well, then why doesn't the water just run off? Why is there even water that's all tilted like that? It would just slosh away. You can imagine an argument back to you that would be like, well, that's insane. Like, how is water curving off? It would just roll off. You're telling me it's like a ball. If I pour water on a ball, it just rolls off the other side. Right? So the point of this is to make the case that this is not a dumb idea, right? And it takes a lot of sort of discussion and thought to disprove even this idea, which is ludicrous, right? It's ludicrous. Okay. So first person that really wrote this. He was not the first person to come with arguments against this. The idea, the arguments for the Earth being a sphere, but he's the first person we have sort of recorded information of him writing down specific reasons for why he thought the Earth was spherical on physical grounds, and that's Aristotle. Okay, we'll hear Aristotle's name a lot in this course because in many areas of sort of proto-science, he is a really key figure. He just had so many ideas and so many thoughts about so many things, and he ended up being wrong about almost all of them. But he was such an influential, and his strength of argument was really impressive. It was more about the arguments that he had than the actual answers that he came up with. But basically, he argued that the Earth, in fact, is a sphere and it's not flat. Roughly, 350 BC. He had a few reasons for this, and one of them was the shift, but another one was this one. And this is a pretty interesting argument. So imagine we lived in a universe that was like a giant snow globe, okay? Or even like this room, okay? It's sort of like this room, except the room has an arching ceiling, right? From anywhere in this room, you can see anything on the ceiling, okay? If you're in that corner of the room, you can see this light. If you're in that corner of the room, you can see this light. I can see it. We can all see it. Doesn't matter where you are. But Aristotle said that's actually not true with the stars in the sky. There are certain stars and constellations that you can see from some cities that you cannot see from other cities. You have to travel pretty long distances to be able to do this, but not impossibly far distances to do it. Okay? So his argument was, like, look, there's some stars and constellation over here, but here I am in Athens, I can't see this. But if I travel, say, farther north or farther south, I can suddenly see a constellation I've never seen before. And his argument was, what's going on is our horizon is limited by where we are on the surface of this spherical thing. And so when we're over here, okay, we can only see out here because the line of sight from this star is blocked by the curving Earth. It's sort of like your idea about the buildings, being up on a building and looking for a distant city. It's sort of like that idea, except now we have a star, which is so bright that I know we can see it from Earth. Okay? No questions about this? The second idea, the second point that he made was that when you look at the moon during an eclipse, okay, during a lunar eclipse, so when the Earth is blocking the sun's light from the moon, it always casts a shadow that's round. So first of all, there's something to think about here. He understood what was going on during a lunar eclipse. He knew that the Earth was casting a shadow onto the sun. He did not think it was some magical thing, right, or it was a bad omen. He said, look, there's something physical going on. You've got the sun. We know it's over here in this part of the sky.